Good day everyone. Today I will present you how collaboration between augmented and virtual reality can support engineering changes in manufacturing systems. I will start with a motivation for the topic, followed by the state of the art. Afterwards, the approach for using augmented and virtual reality in engineering changes in manufacturing systems is explained. I will end the presentation with a short summary and outlook. Due to rapidly changing customer demands, volatile markets, and customized products, manufacturing systems need to be highly adaptable, and this leads to frequent engineering changes. However, the planning and implementation of these engineering changes are often time-consuming and prone to errors. The implementation of these engineering changes also lead to planning errors, which are usually detected too late, and this results again in long downtimes and costs. These risks, together with the often complex evaluation and the short time span that is usually available in industrial practices, lead to the following approach. Our approach is to use augmented reality and virtual reality technologies as they show great potentials. The objectives of this paper is to identify the specific capabilities and characteristics of augmented and virtual reality and then assign them to the single steps of the engineering change process. Furthermore, the potential collaboration forms between these technologies over the whole engineering change process are outlined and the conditions for the implementation are described. So in the first step, the characteristics of augmented and virtual reality are identified, and in the second step, each step of the manufacturing change management process is analyzed and the requirements on a supporting technology are identified. In the last step, the manufacturing change management process is analyzed regarding the collaboration of the technologies. Looking at the state of the art, engineering changes in a manufacturing system can be seen as an alteration made to the factory or its elements that have been released for or are already in operation. There are three possible engineering changes. First, the engineering changes represent the reconfiguration of machines and workstations. Second, machines and workstations are added, substituted, or removed. And thirdly, there can be a change in the network of relationships between machines and workplaces. All engineering changes are managed by the manufacturing change management, and the belonging process consists of three main steps: initialization, implementation, and a follow-up phase. The initialization phase is the starting point for handling all engineering changes in manufacturing, and it ensures a targeted initiation. This phase consists of three process steps. First, the recognition of the need for a change. The second, the analysis of a change requirement. And the third, the formulation of the change itself. The second phase in the process aims at a systematic implementation of the planned engineering changes, and they are implemented within the framework of a change project. The implementation phase consists also of three steps. In the first step, it is about the planning of the change process. In the second, the definition of a change project is done. And in the third, the implementation of the changes happens. In the final phase, there's a focus on the systematic completion of the change and the standardized documentation of the knowledge which is gained in the change project. This knowledge base helps to use synergies and prevent a repetition of previous errors, and additionally, it accelerates future change process. This follow-up phase consists of also three steps. First, the stabilization of the results. Second, the evaluation of the success of the change, and third, the securing of experiences. The extension of the real environment with virtual objects is called augmented reality. It refers to the overlapping of reality with computer-generated virtual information. The objective of AR is to enhance the user's perception of the real world and to enable interactions with virtual objects in the realms of the physical world. These virtual objects may contain further information that is helpful for the user, for example, to complete a certain real-world task. Therefore, AR can be used as a tool to simplify real-world tasks performed by humans. Virtual reality is defined as a computer technology for creating and displaying virtual environments. It consists of computer-generated three-dimensional objects and their temporal dynamics. The objectives of VR are the simulation of human sensory systems, the interfacing of the real world and the virtual environment, the creation of the VR content, and the collaboration of multiple participants with the help of VR. The characteristic of both, so AR and VR, are collaboration, immersion, annotation, and interactions. So if we're looking at the collaboration, for example, AR is used for the collaboration of the real and the virtual world. Therefore, it can be used, for example, for overlaying the future engineering changes on the current manufacturing system to visualize the changes. Virtual reality can be used for the interactions with the multiple participants as well as the collaboration within the virtual world itself. So it seems suitable for e.g. planning, simulating, and evaluating possible engineering changes before realizing them. If we're looking at the second characteristic, immersion, AR and VR create both the impression of being physically present in a non or only partly physical world. This makes it easier to understand the changes, the belonging requirements, the realization process, as well as the consequences of an engineering change in a manufacturing system. Looking at the characteristic annotation, the objects of interest can be highlighted virtually and annotations can be attached to them in order to support subsequent planning steps. For augmented reality, the information can be directly connected to the machines and the real manufacturing system. This allows to create a knowledge base based on real conditions. Within virtual reality, the annotations can be added as well, but they are based on the underlying 3D model as well as an experience of the users. Looking at the fourth characteristic, interactions, the engineering changes are often depending on interactions between involved participants. By visualizing the object of consideration, for example, a certain manufacturing system area, misconceptions can be reduced. With augmented reality, interactions might be more complicated as it requires more investment to connect, for example, several smart glasses to share one view. The interactions with the help of virtual reality are much easier, as for example, a cave are created for the interaction, especially for multiple users. In this table, the manufacturing change management process steps are analyzed and the requirements on the supporting technology are identified. As an example, the process step, analysis of a change requirement, requires a technology which supports in visualizing networks between machines. It also requires a technology which helps analyzing different target states, for example, by simulations. It also has to support in developing the target state of engineering changes, and it shall consider historical data, and it also shall allow an interaction between multiple participants, for example, in workshops. So if we're now looking at the characteristics which are explained before of AR and VR, VR seems more suitable as supporting technology as it fulfills all needed requirements. Still, both technologies promise strengths and weaknesses in different steps of the manufacturing change management process. Virtual reality, for example, is more likely to be suitable in the planning phases. In contrast, augmented reality seems applicable in the implementation and follow-up phase, as these phases require a direct comparison of the initial and the target state. In the next step, the collaboration of the technologies in a manufacturing change management process are analyzed. Based on the previous analysis, which were shown in the slide before, AR and VR technologies can be used parallel in some of the manufacturing change management steps, and they fulfill the requirements in different degrees. So, if the requirements of a step are partially or fully fulfilled, a collaboration of the technologies seems suitable. So, we're having a closer look, and we found 4 steps in a manufacturing change management process which seem to be suitable for collaboration. Firstly, we found a step in the initialization phase, and it's called Analyze Change Requirements. Here, the networks between machines have to be identified, and based on this, the target state has to be developed. Augmented reality is here able to support the visualization of these networks directly within the manufacturing system, for example, by visualizing the material flow. In contrast, virtual reality is more suitable for planning the target state. A collaboration of both enables the combination of the network information and the planned target state of the engineering change. Secondly, during the planning of the change process, the initial state and the target state need to be visualized. Augmented reality is able to provide information directly again in the manufacturing system, such as infrastructure, material flow, and this is usually not shown on factory plans. So for planning the target state, virtual reality seems to be more suitable, as it is based on existing data and information, and it is more convenient to use for the planning task. Thirdly, the implementation of engineering changes requires controlling and testing of the progress. So to check the progress, augmented reality is more suitable as it visualizes the changes directly in the manufacturing system. On the other side, VR is more suitable for the collaboration between multiple participants. So therefore, a collaboration between AR and VR, for example, between smart glasses and a power wall, facilitates the controlling and testing of the progress. So looking at the evaluation of the change success, AR and VR can be used to detect deviations between the initial and the target state. Augmented reality offers the capability to record the manufacturing system and to transfer this information to the virtual reality model, where the deviations can be detected by superimposing models. To summarize, due to volatile markets and customized products, manufacturing systems need to be highly adaptable. During operations, various triggers lead to engineering changes, for example, the addition, substitution, and removal of machines and workstations. Augmented reality and virtual reality offer vast potentials to accelerate these processes. Therefore, we analyzed the individual manufacturing change management process steps with regard to their requirements for supporting technology. We compared these requirements to the objectives and capabilities of AR and VR. And furthermore, we identified 4 possible collaborations between AR and VR in the manufacturing change management process. In the future, an encompassing AR/VR approach is needed to support the engineering changes in the manufacturing. This also requires to link all the individual steps to a central database that stores the historical data and also new information. Additionally, different roles of users of the manufacturing change management processes will have different views on this kind of shared information database. This single source of truth provides all the relevant information that are the foundation for all AR/VR applications for a specific change. This also leads to less errors during the planning of the change process and to a simplification and acceleration of the process execution. So, furthermore, the modes of support and collaboration need to be investigated too, and this in detail by a systematic, in-depth approach. It also evaluates their suitability. Usability will be another important factor. The aim is to fulfill efficiency, safety, and satisfaction requirements for different users and roles, among other things. Thank you for your attention.